We're now recording, which means that we are almost ready. So let's see. What does Louis say? I saw that there is a WebEx link listed during the exam time.
Yeah.
We're supposed to attend that as well, or are we just taking the exam? I would really much prefer that everybody showed up and was present, just like we are now. So we meet and then we start the exam, and in case something happens, it's easier for me to give notice to everybody in the class by just using the chat or sort of unmuting my microphone or so let's do that. Yes, Michael, we did. I just said it. 12th of October. So yeah, do please show up and use the regular class link. That's actually what it is. It's just a regular class link. So let's do that. I mean, you can of course just show up and then mute the thing yet, but keep the chat open or something like that. Right. Any phase 3 question? Any other questions? Any questions? Anything? No? Right. And then I suppose we can start with something else. And last time we did the beginning of, we've looked at the leftmost derivations versus rightmost derivations, and we looked at rightmost derivations in reverse. And we saw that in order to do a rightmost derivation in reverse, really what we have to do is we start by looking at the entire string, and then we say, right, can I find a right-hand side? Actually, so let's write this down because it's sort of important. So to perform a rightmost derivation in reverse, we start with the input string. It's called a W. And then the first step is find the occurrence of a right-hand side of a rule, say alpha, such that W is equal to beta, alpha, gamma, or beta alpha delta, where those are, this really, in this case here, if we're looking at W, beta and delta would be sigma star, but I'm saying sigma union V just because then it's going to work again and again and again as we go along. So we find something where there is an alpha someplace in W, and where beta, we need a rule, A goes to alpha, where beta A delta is the previous step in a rightmost derivation of beta alpha delta, which here is W. Right, so find the occurrence of alpha such that, etc., etc., etc. Replace alpha by A and get a new sentential form. if this form is S, the start symbol, then we're done. Else, try again. And you can clearly see from this that there, when you start with a long program, there's got to be a multitude of different possible alphas. So finding the correct one is not obvious. Let me take this thing that we had here and just, well, basically this is what we have on page 178. But let me just write that one down. So the this is sort of a first attempt to an algorithm. And it says something like R is equal to W, to W's the input. Do something, and basically what we do is exactly what we had on the previous page. If there exists a substring beta in R, so I've got the names of the Greek letters a little bit different now, but that's okay. And here, just keep in mind that substring can have terminals and non-terminals in, so it's not just terminals. Such that B goes to beta is a production in G. That's the one that I called A goes to alpha on the previous page, but you can probably abstract that away as well. R is equal to, well, now we get the exact same thing as we had on the other one here. I just use alpha and gamma. And alpha, beta, oh, alpha B gamma is the previous right sentential form. That's just the same as saying it's the previous sentential form in a rightmost derivation. Then we'll update R to be alpha B gamma. And we shall do that until R is equal to S, where this is the start symbol. Now, of course, if this is not the case, we probably should have said else error there. But that's okay. So what we get is a derivation that says S takes a number of steps and becomes alpha B beta, and these are rightmost, and then it's alpha, oops, that was a gamma, wasn't it? And that's equal to W, or was it R? Now, this beta is special, right? Because the beta is the one thing that we find that we can replace by the left-hand side of the production on which it is the right-hand side, is called the handle. And it's called the handle because there is just one handle, and that is the one that represents the correct right-hand side to find and replace by its left-hand side in order to obtain the previous right sentential form. So let's give it a little go. Let's do an example. And we'll just use this grammar that we've seen a million times before. There we go. And let's see, what shall we do? And let's set W equal to ID plus ID. So what I'd like to do is, if we do a route, we can probably do a rightmost derivation down here. That's probably fairly easy to do, right? So let's give that a go. So it's going to be something like E goes to T, rightmost. E goes to F. Oops, I'm doing full poop. Yeah, E is the start symbol. Rightmost E plus T. Rightmost E plus F. Rightmost E plus ID. Rightmost T plus ID. F plus ID. Can we fit it in? Here we can. We get that. So that's our rightmost derivation. That's all fine. Now can we do this? Can we do this backwards? So if I say ID plus ID, if I want to do a rightmost like a reverse rightmost derivation here, now what I have to do is I've got to find the handle, which is what, whenever I apply the replacement of the right hand side of the handle to its corresponding left hand side, gets me that. So it's pretty obvious by cheating here and looking down here that the handle is there. But it could also be here, or I mean, could it? Well, no, because that wouldn't get me that. So if I want to get this sentential form here, then we have to turn this ID into that one. And that sort of also makes sense, because why were we doing rightmost derivations in reverse? Well, because we wanted to read the input from left to right. And if I underline here, so if I use purple to mean possible handles, then I get that one and I get that one. So let's pick that left hand one because that's the correct one. So actually, let's use this one here. So we'll pick that one and we get F plus ID. This, by the way, is my own handmade notation. The reverse rightmost written upside down, right, left, or right. And no, I'm not going to write F and ID the wrong way around either, because then it just gets confusing. Right, so what are my options here? Well, if I go hunting for right-hand sides, I've got a right-hand side there, and I've got one there. So again, if we say, what are my possible ones, that and that, and if we pick the leftmost one, that seemed to be a reasonable thing to do, then what do we get? Well, F becomes T, so we get T plus ID. Okay. What are my possible ones here? There's that and that. Well, let's pick that one. And then we get E plus ID. Well, now there's only one other possible one. That's this one, so that's got to be the one. So that's E plus F. That's got to be this one. E plus G. There's only that one. Well, no. I have two here, don't I? Which one should I pick? Oh, I forgot to green the ones that I picked here because there were only one. So which one do you want? think they've gone home. Both because they are used in E. No, no, no. You can't do that. You have to pick one of them. If you pick E plus T, then it's that one, and I replace it by that. If you pick T, then I replace that T by E, and you end up getting E plus E. So now you have E plus E, which leaves you stuck with something that you cannot reduce to any further towards the start symbol, which is just a single E, because there are no right-hand sides that have just a single E that can be changed to anything, or a compound E plus E that can be changed to anything. So if I picked just this, then we will get in trouble. So we have to pick the entire thing. But that sort of still kind of seems okay because it's the possible handle that starts furthest to the left, or something like that. That seems to be a reasonable rule. I mean, it seems definitely reasonably obvious, or at least I think so, that if you have a choice between two handles, in a case like this, or actually let's just look at that first one, this one here, then since I'm reading my input from left to right, I should start with the handles that are furthest to the left, because in a rightmost derivation, which non-terminals are handled last? Well, the leftmost ones. So when we do it in reverse, we want to handle those first. So Benjamin says, how do we know that without more than one look ahead, though, that reducing E plus T to E rather than T to E is correct? Well, that's a good question, and we don't. And that's exactly why this is a little bit more complicated than this. Now, what I haven't told you is sort of the scaffolding that we can use here. But what we're going to have to do something where we keep track of states and symbols and stuff. So we need a stack. So at the time, I can reveal that much to you now, and I don't know if that's going to set your mind at ease. But you can answer that when I've told you what it is. At the point that I have this, E plus T will be on a stack like this. E plus T. Now, of course, just the fact that you have that on a stack doesn't mean that it isn't tempting to reduce the T, because T is on top of the stack, but the entire stack makes up the correct handle, actually. So depending on what the input, what the look ahead is, we do different things. But we're going to need some sort of state space to keep track of where we are, and for that we need a DFA of some sort. So we need a stack and a DFA. And what is it when we have a stack and a DFA? That's a PDA, right? A push down automata. So we need to keep track of where we are in this DFA for every one of these states. So it's going to be something like we get E S1 plus S2, oops, T S3. So we sort of have symbol state pairs. But you're absolutely right. Just looking at this, and then you can even say without the look ahead, there's just no way to formulate a rule that always works, because what happens if I have two handles, or two possible handles that look like that? Well, they start at the same time. They're both furthest to the left. Should I pick the shortest or the longest? I don't know. It's not immediately obvious. So here's what we can do: is we can try to formulate this idea that a handle always is the one that is furthest to the left. So let's give it algorithmic attempt number 2, and it's going to look very close to being the same. So we'll start with a stack we'll call it V, and there's nothing on it. And then we'll say repeat. And we're going to repeat something until I have a stack that consists just of the start symbol, or I'm out of input, or there's no handle on the stack. So now we can sort of do what we said before, where we said if there is a handle in R, I think it was R, wasn't it? Yeah, so here we said if there exists a substring in R, which is the handle, here we'll just say if the handle beta is on top of the stack, which it would be, right? Because we're starting, when we look at this, we're scanning for possible handles from left to right. So if this first part here were on the stack, imagine that I was trying to push all this stuff on a stack, and I would stop as soon as the handle appeared on the stack. Then I would stop after that, and then I would replace it by F. Then I would continue on with that one. Oh, sorry, no. Then that would be replaced by a T, which would be replaced by an E. Then I would push plus. I would push ID. Now ID is a handle. I'd replace that by F, and then I'll see that handle, and then I'll replace that by, I'll see that F gets replaced by a T. Now I have the entire handle to replace it by E. So if the handle is on top of the stack, then let's assume that we have B goes to beta is a production of G. Then pop beta from V. So depending on how long beta is, we pop a number of things off, and then we push B on. So basically this just replaces beta by B. And if the handle is not up on there yet, then push the next input token onto V. Keep going until V is equal to S, or we reach end of file and no handle on the top of V. Then we can finally say here down at the bottom, if V is equal to the stack with just S, and we have end of file, then success, else not so much. Okay. So it might be interesting to also just note the following. If during the parse V is equal to, I don't know, x0 up to xn, and the remaining input is, shall we say, AI to AM, then x0, x1 dot 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 xn minus 1 xn followed by AI plus 1 dot 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 AM is what? What does anybody recognize that sentential form there? Where would we find that? Well, we're using a stack, but that doesn't really change what we were doing by simply just replacing right-hand sides by left-hand sides. And every time I replaced a right-hand side by a left-hand side, I took a step, not quite. I took a step in that direction. So in this sort of generic case, this thing here, oops, is one of these, right? So if the string is derivable, this is a right sentential form in the derivation of A0, AM, let's call it W, if W is in the language of the grammar. So by taking the elements that I have on the stack, which can be terminals or non-terminals, and sort of gluing it with the remaining input, then I always get a right sentential form of the derivation of W, if W can actually be derived by the grammar. So there's a definition I want to show you now. I don't want to say much about it. It's sort of a little complicated, but it doesn't matter. But I just want to, and it's definition 4.6, which is called a viable prefix. And the idea of a viable prefix, well, I'll write it down here. A viable prefix is, well, it's one of two things. It's a prefix of a right sentential form. So one of these guys, right? That's the right sentential form. What's the prefix? It's that or that. So something that starts at the very left and goes in. Oops. Let's go. There. Right, so it is a prefix of a right sentential form. That does not continue past the right end of the handle of that sentential form. And this sounds really complicated. It really isn't. What this says is basically, well, it says the following here: a prefix. Then I'll come back and explain it again. A prefix of a right sentential form that can appear on the stack of a shift reduced parser, which is the parsers that we're about to look at. So before I explain this, let's just go back to this slide here for a second. And I just want to put a name on this. This reduce, and this is shift. So the idea of shifting is just moving things from the input onto the stack. And the idea of reducing is recognizing that we have now found a handle and replacing it by its appropriate left-hand side. Now, let's just quickly read this top one again. And it says a prefix of a right sentential form that does not continue past the right end of the handle of that sentential form. That sounds like gobbledygook in some ways. But here's what it is. If I looked at this entire thing and I say, is that a viable prefix? No, it isn't, because it continues past the right end of the handle, and the handle is this. So the only viable prefix of this is that much. Now, why is that important? Well, it's important because if I kept going and I ended up with this thing on the input, then I could very much be tempted to say, okay, that ID can become that F. And if I do that, then I might get myself into trouble, because I know that that I want. We know that the handle we're looking for is the furthest possible handle that's to the left, and then we might have to deal with some issues with possible overlaps and what have we not. But if this is to work, where the handle is on top of the stack, then it is indeed true that this viable prefix is going to be what's on top of the stack. Well, the handle is going to be on top of the stack, if we promise that the viable prefix never extends past the handle. If the viable prefix extends past the handle, then we can keep putting things onto the stack and sort of bury the handle down below. And we don't want to do that. We want to keep the handle, when it appears, at the top of the stack. And that's exactly what it says right there, right? It's a prefix of a right sentential form that can appear on the stack of a shift-reduced parser. So we want to make sure we don't get too much. We don't want to get too much stuff on top of our stack and therefore bury the handle. Right. So let's. Any questions or comments or anything right now, or can we move on to? There's a few definitions here that we sort of have to throw out. We don't have to throw them out. We're going to do them. Could you say again what V equals S means? Yeah, that's just that the stack has just the start symbol on, right? So the stack contains one element, which is S, which is the start symbol. So that means you've managed to go from the input all the way back to the start symbol, right? So in this little example here, we started out with that on the input, and because we took all these steps, we end up with just that on the stack. If we try, I know this is a little premature, but I sort of want to show it to you. So if I do input stack, then we have ID plus ID there. Then what we do is we get ID, we get plus ID there and an ID there. And now we replace that ID by an F. We still have plus ID there. Then we replace that. We still have plus ID there. Then we replace that, and we still have plus ID there. Then we get E plus. And now there's no more input, so we're down to the end of file. So we get E plus ID. Still that, we get E plus F. Still that, we get E plus T. Still that, and we get E, and then we're done. Which is why so what does Benjamin say? Which is why that would be the end of the file, because you've collapsed it down to just a start symbol. Yes. So if you've collapsed everything down to, or reduced is a better word to use, if you've reduced everything back to the start symbol, then for that string that originally appeared on the input to have correctly been reduced to the start symbol, you better be out of input as well, because if you have more input, you're sort of in trouble, because the start symbol normally does not appear on the right-hand side of any rules. So there's not much you can do, and that just means you have too much input. So you kind of have to check that as well. We do that in the recursive descent parsers as well, right? Once we've parsed the right-hand side of the start symbol, we check to see if we have an end file. So nothing super complicated there. Right. So the first one. So this is items. Item sets. And the SLR parsing automata. So let's just throw ourselves into it. 4.7, which is the definition of an LR0 item. Now, the point of an item is to say, right, I'm working on a rule, and I've done some of it, and the rest of it I haven't done, which will denote by separating the right-hand side into two parts, the part that we've done and the part that we haven't done, and we put a dot that sort of signifies where we've gotten to. So if we say let G be a context-free grammar and A goes to alpha, a production, an LR0 item of A goes to alpha is A goes to alpha in brackets with a dot somewhere before, after, or within alpha. So if alpha is more than one thing, you can distribute the dot in there. And we can do a quick example down here. So if I have A goes to A, B, C, E. You thought I was going to say D. I went to E instead. Then we have the following items. So the question is, how many different items can I make? Well, I can make the item where I put the dot here. A, B, C, E, D. I can move it over one. Then I can move it over one again. And get my E's and D's straight. And A goes to A, B, C dot E and D. A goes to A, B, C dot D. The other Ben once tried to do this with the entire espresso grammar until somebody reasonable stopped him. I think that was you, wasn't it?
It might have been.
He was a good page and a half into it, and you were like, dude, that's going to take like 7,000 pieces of paper. He would have been at it still if he were doing that. It would have been quite a poster.
I think I actually said, Ben, don't you have a thesis to write? It was when I was taking compilers. Did you have a thesis to write? He's like, oh yeah, that's right.
Yeah. So we have something like that. So let's just see if we got it right. 1, 2, 3, 4, 5, 6, which is 1, 2, 3, 4, 5, one more than the number of symbols on the right hand side. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We got them all. Right. So that's just a quick little definition. And another one. This is the stupidest definition that you'll ever see. An item set is a set of items. Right. So, yeah, not particularly complicated. Now, what I want to do now is I want to define an NFA, because we all know that making NFAs is a lot easier than making DFAs. So we'll go on to the next page because we need all the space we can get. So we'll do definition 4.9. And what we're going to do is we're going to do a viable prefix recognizing NFA, because it turns out, and I didn't prove that to you, that the set of viable prefixes for context grammar G is actually a regular language. So let's actually write that down. So that came as a surprise, right? So, oh, he ate too much cake. He's a little fat. The set of viable prefixes for a context-free grammar G is regular. Yes, to understand recursion, you must first understand recursion. But this is not particularly hard to understand. This is stuff, all of this stuff is just basically using all the 456 knowledge that you have already forgotten.
Recursion is just fancy iteration.
With a stack.
Fancy iteration.
With a pile of junk on the side. Right, so let's see. Let's define now. So let G be V sigma PS. All right, let's just identify what's what. Those are non-terminals. Those are terminals. That's the star symbol, which happens to be in V, and these are the productions. So that's V by V sigma star. Actually, that could be an epsilon. So let's not worry about that. Okay, there we go. So what we're going to do is we're going to let that be a context-free grammar. Now define a new one, an augmented one. And what we're going to do is we're going to ensure that there's a single start symbol. So define G prime by adding S prime goes to S, where S prime is not in V. So it's a new non-terminal to V. Or by adding S prime to V, and S prime goes to, that looks a little stupid, shall we just clean that up a bit? S prime goes to S to P. So basically we get G prime is, well, it's V with this new start symbol added. It's the same terminals. It's P with another rule that says S prime goes to S. And then it's this new start symbol. So now we have a context-free grammar in which we have a left-hand side, or we have a start symbol that appears once and only once on the left-hand side of the starting production. If we already have a situation where that's the case, then we don't have to do that. So let's now create an NFA, and we all remember what an NFA looks like, right? It's something like Q, V, sigma. So the V and the sigma here are, of course, the terminals and the non-terminals. We have a transition relation. We have a, what's Q0 again? Start state and a set of final states. So those are final states. This is start state. This is a transition relation. These are my states, and that's my alphabet or my symbols, right? So where Q is a set of items for G, oh, Q is the set of items. So we'll define that as the set of items of G. And we've already seen what an item is. It's just a production with square brackets around it and a dot somewhere on the right. And so it's a set of items. It's the set of items of G plus Q0, which is not an item. That's just a start state, right? The final states. Can I change the color on something in here once I must be able to. Color, yeah, there we go. Right. So what are the final states? Well, the final states are all my complete items. Now, we didn't write that down, did we? We can do that here real quick. A complete item has, so a complete item has the form A goes to alpha dot. So it's all the ones where we have the dot all the way to the right. And if I use this dot to keep track of which part of the right-hand side have I dealt with and which part have I not, if the dot is all the way to the right, then there's nothing more to do for that particular production, for that particular right-hand side. I've dealt with the entire right-hand side, and what I can do is I can say, well, I've now recognized something that is equivalent to alpha, or something that is alpha, and I can now replace that by the left-hand side A. Now, of course, if you're thinking, well, wait a minute, does that then mean that this is equivalent to alpha appearing on top of the stack and being the handle? Then the answer is yes, that is exactly what it means, and that's exactly what you should be thinking. So once I've managed to travel the dot all the way to the right, then I know that there's going to be a handle on top of the stack, and I can do a reduction. And if I can make an NFA and then eventually turn it into a DFA, then if I just play along in that automata, or automaton, I guess it is, then if I ever end in a state where I have a dot all the way to the right on an item, then it means that that handle is on top of the stack. Now we're officially out of coffee. Now we're going to slow down, right? Oh, yours is empty too. Is that mine as well?
Yeah.
Is that from last time?
Yeah.
It's not going well. We have no more caffeine. We're in trouble. Right. Well, we'll soldier through. It's only another 20 minutes. So the final states are, we need to do this in red. The complete items G. So we know what Q is, we know what V and sigma is, we know what the start state is, and we know what the final state is. So now we just got to figure out what are these, or what is delta, the transition relation. So if we think about it, we gotta wait. We have to get away, or we have to have a way to get started. So we need to be able to get from. We have to have a way to get from this Q0 to this state, sort of. Actually, to the state that contains the item that looks like that, because that's the item that says, I haven't done anything at all yet, but I'm ready to go. So we can put that in as the first one. And that one basically just says, if you are in Q0, then without consuming any input, you may go to the state S prime goes to dot S, where S prime goes to S is in P, and remember P is just here, so it's just this guy here. Actually, it's not in P, it's in that part there. So saying that it's in P is really not all that. It's not really true, is it? No, it's not. Yeah, close enough. It fails a little bit, but that's okay. Now, can we just let me just ask that question real quick here. If I've gotten from some start symbol and I've derived myself to something that looks like alpha, x, beta, and let's say that the dot is right here. So I've dealt with all this stuff down here. That's fine. And the next thing I need to do is this x. Then what are my possible steps here? Well, if x goes to alpha 1, alpha 2, alpha 3, then my next step could be, well, actually, let's not call them alpha, let's call them beta 1, beta 2, beta 3. Then it could be alpha, beta 1, beta, alpha, beta 2, beta, alpha, beta 3, beta. So basically, I can replace that x by one of its right-hand sides. But I still sort of get the dot right there because I haven't done anything yet, right? So in order to get on with this thing here, then I got to take care of one of those right-hand sides. So we can certainly say that if I have a situation where, oh, we need to put brackets around these, where I've done something, my dot is in front of a non-terminal, so we get something like that. Then without eating any input at all, then I can say, right, well, this is just equal to B goes to dot gamma, where B goes to gamma is in P. So if B goes to gamma, oops, God damn it. If B goes to gamma is in P, then when the dot is in front of this capital B, which is the left-hand side of this rule here, then I can go to a new state in which I'm going to work on this guy here. Now, of course, at some point, this dot is going to travel all the way down to here. And then I might want to come back to this state here and say, ha, now I've done a B, and I'll just move that dot 1 over there, right? And that's the next one. And that's the last one. And that's the situation where A goes to alpha. And here I'm going to use an X because the idea of moving the dot over to the other side here in this situation was that I said, right, if I got to go do this, so imagine that your dot is coming around here and it ends up there and it says, ha, I'm in front of a non-terminal. That non-terminal exists on the left-hand side of a rule. So in order to move on, then I better go and parse whatever that non-terminal requires me to do. And that means starting here. At some point, that dot is going to travel all the way down here. And now I can come back to the situation where it says, okay, I've actually done a B, move that dot 1 over. But if this had been a terminal, then I can also move the dot 1 over simply by moving that terminal onto the stack. And we'll capture that, both of those situations, by this third rule here. So basically that says if I do an X, whatever that means, well, doing an X means if X is a terminal, moving it onto the stack, and if X is a non-terminal, do one of its right-hand sides. And now you can see probably why this stack that I need has to be a mixture of symbol, state, symbol, state, symbol, state. Because if this is a particular state, and in an NFA I can transition out of that state without consuming any input, come to another state, and do a whole bunch of stuff and end up in another state where the dot is all the way here, then how am I going to find my way back to here so that I can now move that dot over onto the other side using the third rule? Well, I got to keep track of what states I'm in, and that's what we do with half of the space on the stack. But we'll come back to that in a later time. So here you can see the dot was in front of the X, now it's on the other side. This will be a lot easier to understand once we get an example going, which we will do in just a second. So let's try to do an example, and let's use S goes to E. E goes to E plus F, or F. F goes to ID, or bracketed E. And let's see, rule 1. That says delta on Q0 and an epsilon is the state S goes to dot E. I didn't put in a new start symbol here, but I probably should have, but it's okay. We're just trying to keep this down. Oh no, we didn't need to because S is not on the right hand side, so it's all good. Right, so rule 2. Now what was it that rule 2 said? Rule 2 said that every time I had an item, so every time I have a state, because every state is an item, remember, see, look, the states here are items of G. So every time I have an item with a dot in front of a non-terminal, so here, that one, then I can transition on an epsilon to a state that is just one of the productions with E on the left-hand side and the dot all the way to the left. So if I look at this one here, I could have a dot in that situation here, 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 and there. So let's write those down. So I can do this. So if I have S goes to dot E, then I can transition on an epsilon. Well, what can I do? I have two options. I can do this one or that one, right? So this is equal to E goes to dot E plus F, or we need both of them, right? Because whether I parse an F or I parse an E plus an F, both of those reduce to just an E, so they're both equally good. What else? Then we have, well, we have the one with the dot there, 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 and there. So let's just write them down. E goes to dot E plus E on an epsilon is, well, I get the same ones up there, don't I? We got that, and then we had E goes to dot F. Oops, forgot the epsilon. Well, that's just F goes to dot ID, or I skipped one, didn't I? Yeah, I did. We'll have to come back to that one. There. I skipped the one with the dot there, but we'll do that one now. E goes to E plus dot F on an epsilon. And that, of course, is F goes to dot ID, and dollar E goes to E plus dot F epsilon is F goes to dot E. There we go. Then we just have, we still have a few left, don't we? We have dollar, let's see, how many do we need? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many have we got? 1, 2, 3, 4, 5, 6, 7, 8. Oh, good, we only got 2 left. So that's got to be F goes to bracket dot E on an epsilon, and of course that's just E goes to dot E plus F. And finally, Ben is already looking at his watch thinking, when is this nonsense going to end?
Just making sure that it's not
So there we go. Those are all the rule 2s, right? Now what about rule 3? So rule 3 are all the ones where I can place a dot not all the way to the right. So it's going to be there, 3, 4, 5, 6, 7, 8, 9. Yeah, 9 is correct. So S goes to dot E on an E is just S goes to E dot. So this is just a traveling dot rule. So here we need E goes to E dot. We need the dot there. E plus F on an E is E goes to E dot plus F. E goes to E dot plus F. And a plus, we'll move the dot onto the other side. What we'll see real soon is that we never ever have to write all of this nonsense down, because we can, by simply glaring at the grammar with half an eye shut and the other one looking skywards, just write down the DFA without any problems. And people always find this really, really scary, and everybody always gets it right in the end anyways, because I'm so good at explaining it. Yeah? So there we go.
They're just so scared of getting it wrong, they actually practice.
Yeah, maybe that's what it is as well. Practice makes perfect. So he goes. I remember when I before I wrote the book, I thought this was complicated to teach people, but I suppose the best medicine, if you think something's complicated, is try to teach it to somebody who really don't understand it. So here we are. This could all be an illusion. I could be making this up as I go along. Well, that happens. That does happen sometimes, but that's just how it is. I could also try to get my brackets right. This is a little tedious. This is where we should have some of that, oops, the ability to just speed me up and then play some funky music.
That's why I always watch lectures back at 2 times speed.
Well, you play an instrument. Could you bring something in next time?
I was a choir boy. What are you talking about?
Oh, you can't play an instrument?
I could play piano and guitar for a while, but
well, just enough, sort of like to speed me up. No. So what we can expect some angelic whining of a sort.
Well, no, it's even more. It's worse than that because I was a bass.
Oh.
So feel like.
Oh, so we're sort of talking about like Ivan Rebrov kind of stuff, yeah. Right? Okay. No, that's okay. He's good. Nobody in the class will know who he is. Does anybody here know who he is? I'd be surprised. There we go. So what we have here is we have, that one dot all the way there, dot all the way there, there, dot all the way there, dot all the way there, dot all the way there, and there. So we really have all these different possibilities. So what you can do now, which we unfortunately don't have time to do, is we can finish this example. This is example. Oops. 4.23, because what I have now is I actually have the entire definition of an NFA, and I can write down that NFA, and I'll do that next time. And then we'll see that we can turn that NFA into a DFA. Actually, we know we can turn any NFA into a DFA, but we'll do it, and then we'll ponder a little bit, and then we'll say, all right, to hell with the NFA, because we can do the DFA directly from just looking at the grammar. And we're going to do that by taking the epsilon closure operation that we have in NFA to DFA, and we're going to apply that to the set of items in the resulting DFA directly, and that way we don't have to go via the NFA, and it becomes super fast to actually do this. So to do the DFA for this particular grammar here will take all of 2 minutes, something like that, rather than all this nonsense that I've gone through. Any questions? If not, remember, if you're looking for a partner, send me an email, and we'll sort something out. Office hours tomorrow, as usual. Oh, before you run off, I got an email from Ben today about a script. Is that ready to be released?
Mm-hmm. I mean, it definitely was before, but it's the one I was telling you about where it would run all of the tests.
Yeah.
I did modify it so that you could cherry pick which test sets you want to run.
Okay.
And so Alex's video that he made that I actually didn't know about.
Oh, I forgot about that. Yeah. Somebody mentioned Alex's video. Thank you very much.
Making my own video when I saw that email.
Did you not continue with that then?
No.
No?
Because his video is fine.
Yes, but that's
exactly the same.
Okay. So are you going to so to this script that you have now, does that spit out a grade at the end?
Not yet. No.
Okay.
Well, and that's because we still need to decide how we want to do that grade. But the grade is essentially going to be
proportional to the number
of tests. But if the number of tests that failed all exhibit the same error, then you can deduct like only 5 points from your one.
Okay. So what's the main difference between your script and Alex's script?
Just those cherry-picked options.
Okay.
That's pretty
so cool. It's an AutoGen 3.1.
Sure.
Or something like that.
Sure.
So are we going to make that available?
Yes. I can make
on
that available on
canvas? Okay,
yep.
fine.
In the same place as the phases.
Yeah, okay, so it'll be in the phases space. Right. Done and dusted for today, unless somebody has anything to say. It's been you guys have been very quiet today. I don't like that. Maybe you guys need to drink some coffee or Coke or... What do you mean your hand hurts? You should try having mine. I have a bad thumb from a motorcycle accident. Nicholas, why haven't you slept? You're not supposed to. What have you been doing? Well, maybe we shouldn't be asking that. Well, so sometimes you shouldn't ask questions that you don't want to know the answer to. Stress. Listen, I have never been stressed in my life because when you get stressed, you don't get anything done. You just sort of run around in circles. And that's probably so no, there's really no, so there's no, first of all, there's absolutely no reason to fear the midterm because it's a freebie, right? So it covers up to and including what we did up to last week, none of the SLR parsing stuff we did today and last time. But if you think of the midterm, it is a chance to get 10% of your grade. If you bomb it, then you can throw it away and you can do better on the final anyway. So there's really nothing to be worried about now. It's not until after the midterm when you realize that maybe you should have studied a little bit more that you can get worried. But it's not like a bad score on the midterm means you're screwed forever. Absolutely not, because you can choose to disregard, or we will automatically choose to disregard your midterm score if your final is better percent-wise. So I don't think there's any reason to stress out about the midterm. I think midterms are stupid anyways. And I don't even know why we're doing them. Maybe we should just stop doing that. Oh, no, then people will complain about that as well. Clarify the format of the test is on Canvas during class time. Yep. Do we need to be in the WebEx lecture during that test? Yes, please.
And it's just the quiz tab.
So show up here.
You don't need lockdown.
No, show up here, and we'll set the exam to start at 4:05 or something like that, because then we just have enough time for, a song or something we can, do together.
One way or the other. I was actually going to ask.
We used to do that in Denmark all the time. We would sing at the beginning of class. It's nothing to laugh about because it sounded absolutely wretched. But in my English classes in business school, my teacher always said, you people know shit about Danish culture. We're going to sing. So he forced us to sing in class. Yeah.
I learned some very rudimentary African Tagalog.
Oh, Tagalog? That's not African.
Is it not?
No, that's Filipino.
We
need to teach him geography.
I'm just pulling Tagalog out of thin air.
All right.
No, it was basic African.
Yes. So Louis says that Tagalog is indeed Filipino.
Yeah.
And Janelle can verify that as well. And I knew that as well. Remember, I'm European. I know geography. Which, oh, by the way, I can recommend the guy that plays GeoGuessr on YouTube. He's fun to watch and amazingly good. Anyways, we're out of here, so I'm going to stop recording.